Cool, thank you. So the phylogeny of mammals has been one of the sort of major questions in systematics for over 100 years, and the debate or the evidence over the sort of the 19th and the 20th century was very much driven by paleontologists, people like Gregory and Simpson, and later with the adoption of formal cladistic methods, people like Malcolm McKenna and Mike Novacek, among others. And although there were molecular studies over the course of the 20th century, starting surprisingly early, someone wants to sort of teleconference in. So that was the debate. It was really driven by paleontologists, except when you go into the early 2000s, there were two really key papers. I remember them coming out when I was in my final year undergrad, and you had the same edition of Nature, and you get two teams working more or less independently with essentially independent data sets, quite big by the standards of the time, and they more or less get exactly the same topology, almost exactly the same phylogeny in terms of the relationships between mammals, specifically placental mammals. And what's been interesting is over the last, subsequent 17 years, there have been many papers, but more or less they've essentially confirmed this arrangement. We have a consensus. I apologize to Rob Asher. I'm going to call it molecular consensus because it's based on molecular data. But it is a consensus. And as far as morphology goes, we can be quite happy because it supports the monophyly of most of the orders. Two major exceptions. Whales fit within Artiodactyla. That is less surprising nowadays when we've got a much better record of fossil whales. And we have a split of insectivores or lipotyphlans. There are two independent radiations of insectivores within placentals. But what was surprising is that there are four fundamental major clades, four superorders, Xenathra, Aphrotheria, Euarchontoglires, Laurasiatheria. Xenathra was basically recognized based on morphology or by some morphological studies, but the other three really were not. But this molecular-based phylogeny is extremely strongly supported. We can quibble over some nodes, but this overall topology is unlikely to change. This is, as far as we can tell, this is the truth. And possibly the most interesting thing is if we compare the two groups, Laurasiatheria and Aphrotheria, is we see a huge amount of convergence of broad ecomorphotypes. So we get mole-like things, we get hedgehog-like things, we get shrew-like things, ant-eating specialists, ungulates in inverted commas, and they all appear morphologically really quite similar. But the molecular data says that these are convergent. So what does the morphology say? In the light of this, subsequent studies of morphology, which have massively improved in terms of their rigor, in terms of the characters, and the one that's really important is O'Leary et al. 2013, which was a huge sort of genuinely phenomic study, 4,000 characters, 4,500 characters from all sort of partitions of the body that we've talked about, representatives of all orders, lots of fossils. They added in molecular data as well. It's a really great resource, a huge effort. I think people on the team are now talking to each other again. And when they analysed it, so the left-hand picture is their combined analysis. And I'm not going to go into the detail, but say broadly it does agree with that four superorder framework. But if you analyse the morphology just on its own, so I've colour-coded the branches according to the four superorders, the morphology on its own clearly fails to recover that arrangement. And we get insectivores grouping together. We get ungulates, in inverted commas, grouping together. We get ant-eating forms grouping together. And we get people, molecular people in particular, saying nice things like, this shows the inadequacy of morphology for higher level mammalian phylogenetics. It's inadequate. It's not going to work. And of course, as Roland alluded to, this is a problem, particularly when we're interested in fossils. So if this morphology fails to reconstruct key relationships amongst living mammals, why should we trust the relationships of the fossils? So, for example, there's a fossil Leptictis. In the combined analysis of O'Leary et al., it comes out as an Aphrotherian. Is it an Aphrotherian? Cynopa is a carnivorous, it's a hyenodont. It comes out near carnivores, carnivorans, so things like cats and dogs. Is it a carnivoran? And this is a problem because fossils are critical for comparative analyses of biogeography, trait evolution, things like that. This is great because it keeps us in a job. Because we, molecular people need us because they genuinely do, including fossils, does improve estimates, provided, of course, those fossils are in the right place. So, are we doomed? This bothered me, still bothers me. I don't wake up screaming in the middle of the night. I got over that after a few years, but it does bother me. So how do you improve congruence? How do you sort of resolve this? And we can look at methods, so we can do our nice fancy Bayesian analyses. We can do tip dating. Characters, we can maybe add more characters. I think looking at non-independent and correlated characters would be important. And we can improve taxon sampling. Or, there's a sort of false dichotomy or trichotomy. We do all three. The Lewis model on its own, the Bayesian approach or likelihood approach for morphology doesn't solve the problem. Tip dating doesn't solve the problem. I've got some unpublished analyses, doesn't work. More characters, well, I think the O'Leary et al. Will be very insulted. If I'm 4,500 characters, you're not going to suddenly pull out a huge number more. As I say, non-independent or correlated characters, that would be really, really important. And it's very old-fashioned, but let's have a look at taxon sampling. There are lots of studies by people like John Weens and so on, who've shown that, yes, in general, if you improve taxon sampling, you improve phylogenetic accuracy. And this is a classic paper, 1988, Gautier et al., who looked at a specific case, and that was the relationship amongst amniotes, and they showed that synapsid fossils are really, really important because if you only look at the extant ones, you get a warm-blooded clade. You get birds basically grouping with mammals. But if you include synapsids, because they have this combination of primitive and derived character states, it basically solves the problem. You get the birds grouping within diapsids as they should, and the mammals more distantly related with these synapsids. So the fossils are really key because they have this combination of primitive and derived characters. And fossils clearly do have a major effect on the O'Leary et al. Dataset. If you take all the fossils out, you get marsupials within placentals, which is kind of scary. But fossils are clearly having a major effect on the topology. So is it the case that if we have the fossils with these combinations of primitive and derived character states, is that going to be enough to switch us from the incorrect, and I genuinely do think it is incorrect, morphological tree to a phylogeny that agrees with the consensus, with that 4 superorder arrangement? And of course, we could go out and find a whole load more fossils, absolutely, and we should, and that's what we should be doing. There's a lot. So there's a nice paper, 2017, they estimated 150,000 fossil species from the Cenozoic alone. That's a couple of PhD projects at least. I'm going to talk about that fossil on the right-hand side in a bit, but of course, is that going to work? There we go. It's a bit slow. I'll come back in 50 years and we'll make a decision. It's going to take a long time. Can we at least investigate in principle whether finding the fossils is going to solve our problem? Can we test it in principle? So my idea was, if this consensus is correct, then there must have existed ancestors for each clade in this consensus. There must have been an Afrotherian ancestor. There must have been a Laurasian ancestor. Laurasio-Therian ancestor, and all the other nodes. Now, if we had those ancestors, in an ideal world, we find our ancestral Afrotherian, is that going to be enough to move our morphology-only analyses over to make it congruent with the consensus? And we can make a guess at what those ancestors look like using ancestral state reconstruction. So this is one aspect of the O'Leary tree. They made a really nice estimate about what the ancestral placental looked like. And they said it had this number of teeth and this shape of ear and all that kind of thing. So I thought, well, you can do this for all the nodes in the consensus. You can essentially simulate or infer what those ancestors would have looked like. So these hypothetical ancestors, this is, again, I want to say this is a principle. This is a test of principle. So if we reconstruct those hypothetical ancestors and put them back in the morphological-only tree analysis, what kind of tree do we get? So that's basically what I did. I took the O'Leary et al. Matrix, made some modifications based on a recent paper by Carrillo and Asher, deleted the constant characters, wasn't interested in them, so leaves us with 4,134 characters. And they did ancestral state reconstruction for all nodes in a molecular tree that matches the consensus. The tree, the details of the tree are not that important, but that's what the topology I used. And I used two different forms of ancestral state reconstruction, one using maximum parsimony and one using a maximum likelihood approach. So we then have, for every single node in that consensus, we have a reconstructed ancestor, or a predicted ancestor. I'm going to call it a predicted ancestor, pseudo-ancestor, hypothetical ancestor. Okay, so let's add those back in to the morphological matrix and then analyze it. So our morphological matrix with our predictive ancestors included. And again, we'll use maximum parsimony for our maximum parsimony ancestral states, and we'll use maximum likelihood for the matrix with the maximum likelihood ancestral states. And then we can compare our fit with the molecular consensus. And we can use standard metrics, things like Robinson folds, and we can also look and say, well, do we reconstruct that overall consensus? And what do we get? Oh, no, hold on. Jumping ahead. We should have practiced this. Obviously, fossils don't preserve completely. So as a sort of test to investigate incomplete preservation, the initial set of ancestral state reconstructions are for all characters, so including soft tissue. So let's see if we don't include any soft tissue, so skeletal characters, then throughout the postcranial, then throughout the cranial, so we only got dental. Okay, so then we basically have characters, also is a bit more sophisticated. We say, okay, well, which characters are scored in at least one real fossil taxon? As a sense of, these are the ones that really possibly could preserve. And what about ones that are scored in half of the real fossil taxa? It's like a sort of average preservation. Ta-da! So this is a morphological-only analysis. No constraints, no scaffold, no molecular data. If I include the maximum preservation, so the best we can hope for in terms of fossils, in terms of predicted ancestors, we get they really want to know. So all 4 superorders are recovered as monophyletic. Within Aphrotheria, we get tenrecs, and we get aardvarks, and we get elephants forming a clade. In Laurasiatheria, we get ungulates, we get pangolins, and we get insectivores, all forming the Euli petifilin insectivores forming a clade. Let's take a worst-case scenario or a less ideal scenario where we only have dental characters. If we only have dental characters for our hypothetical ancestors, we don't get completely the right answer, but we still get some quite interesting results. Aphrotheria, we don't get completely monophyletic. We get aardvarks grouping with a whole load of other taxa which have very reduced or absent teeth, possibly as you might expect. But even then, you still get tenrecs and elephants forming a clade, to the exclusion of horses and hedgehogs. So that's just a summary. So certainly with maximum preservation, you get all 4 superorders as monophyletic. So in principle, improvements in taxon sampling, that might be enough. That might be enough to switch us from the current morphological-only results to a situation that is essentially congruent with what the molecular data is telling us. There exist, at least hypothetically, ancestors with combinations of character states that could link ungulate type, insectivore type, edentate type, Aphrotherians and Xenarthrans. Loads of caveats. So I did the analysis, the analysis with the method I used to reconstruct the ancestral states. I assumed they were genuinely ancestors. I included all analyses, all ancestors for all nodes, and I haven't checked whether they are biologically plausible. How realistic is this? Very quickly, this fossil, transitional between insectivore-like and ungulate-like Aphrotherians. So these kind of taxa might be out there. So what are the prospects for using morphological data to accurately resolve interordinal relationships within mammals? I would say at the very least, don't panic. For those who say that morphological data is sort of intrinsically inadequate for reconstructing mammal phylogeny, I would say that's probably not wise. Thank you very much.